The Disappearing Spoon, and Other True Tales of Madness, Love, and the History of the World from the Periodic Table of the Elements, by Sam Kean. Introduction. Imagine you're at a dinner party, a rather formal one. The kind with fancy tea and tiny spoons. You stir your cup, the steam rising, and as you lift the spoon, it vanishes. It simply melts away into your tea, leaving you with a handle and a look of absolute bewilderment. Your host, a chemist with a playful streak, just smiles. You've just become the victim of one of the oldest, most delightful pranks in science, courtesy of an element named gallium. A gallium spoon, you see, looks just like aluminum, solid and sturdy. But it melts at just 84 degrees Fahrenheit. The heat of your tea, or even the warmth of your hand, is enough to make it disappear. This little magic trick is the perfect entry point into one of the greatest storybooks ever written. And I'm not talking about a work of fiction. I'm talking about a chart that hung on the wall of your high school chemistry class, the periodic table of the elements. Today, we're going to journey through an incredible book, The Disappearing Spoon by Sam Kean. This isn't your typical science book. It doesn't just tell you what the elements are, it tells you who they are. It reveals that the periodic table is not a boring catalog of substances, but a rich tapestry of human history, full of passion, adventure, betrayal, and genius. It's a storybook of our world, and each element is a character with its own tale of madness, love, and war. Sam Kean has sold millions of copies of his books, and The Disappearing Spoon is a modern classic that has captivated readers by showing them that science is, at its heart, a profoundly human story. He was a physics major who found his real education not in the equations, but in the stories his professors told. Tales of explosive sodium thrown in rivers, of Gandhi and Godzilla, of scientists experimenting on the pacemakers inside their own chests. He realized that behind every symbol on that famous chart, there's a story waiting to be told. So, my promise to you today is this: by the end of our time together, you will never look at the world the same way again. You'll see the elements not as abstract letters and numbers, but as the building blocks of history and human character. You'll understand how a simple chart can explain the rise and fall of empires, the secrets of the sun, and even the madness that drives both artists and scientists. We're about to peel back the layers of the periodic table and discover the universe of stories hidden within. Book summary. Let's begin our journey where all great adventures start, with a map. The periodic table is our map of the universe. At first glance, it looks a bit like a lopsided castle, with tall turrets on either end and a long wall connecting them. It has 18 columns and 7 rows, with a little landing strip of 2 extra rows at the bottom. Each brick in this castle is an element, a fundamental substance that can't be broken down by normal chemical means. There are over 100 of them, and the entire structure of our reality rests on them being exactly where they are. The most important rule of this map is simple: an element's geography is its destiny. Where an element lives on the table tells you almost everything you need to know about its personality. Let's start on the far right-hand side, in column 18. This is the home of the noble gases: helium, neon, argon, and the rest. They're called noble for a reason. Think of them as the aloof aristocrats of the elemental world. They are perfectly content on their own. You see, every atom has shells of electrons, like layers of an onion. And atoms are happiest when their outermost shell is completely full. The noble gases are born this way. Helium has 2 electrons, which perfectly fills its one and only shell. Neon and argon have 8 in their outer shells, making them perfectly satisfied. Because they are so stable and self-contained, they have no need to interact, bond, or react with any of the other elements. They are the chemical monks of the universe, incorruptible and serene. For this reason, they were the last to be discovered. No one even knew they existed until the 1890s, because they simply refuse to associate with the common riffraff of the periodic table. But this peaceful kingdom is surrounded by chaos. Just one column to the west, in column 17, live the halogens, like fluorine and chlorine. These elements are the most reactive gases on the table. They are the bullies of the neighborhood. Why? Because they have 7 electrons in their outer shell. They are just 1 electron short of that perfect, stable number of 8. And they will do anything to get that final electron. They will beg, borrow, and, most often, steal it from any unsuspecting element that comes near. Now, if you imagine the table wrapping around like a map of the world, where the Far East meets the Far West, you'll find column 1, right next to the noble gases. Here live the alkali metals, like sodium and potassium. And if the halogens are bullies, the alkali metals are dangerously generous. They have just 1 lonely electron in their outer shell. All they want in life is to get rid of it so they can expose the full, stable shell underneath. This makes them incredibly reactive. Some of them, like sodium, will spontaneously burst into flames if they touch water. You can see the natural partnerships that form. An alkali metal, desperate to give away an electron, meets a halogen, desperate to steal one. It's a match made in chemical heaven. Sodium gives its electron to chlorine, and they form a strong bond, creating sodium chloride, the table salt you sprinkle on your food. This dance of giving and taking electrons is, in essence, the story of chemistry. Atoms are constantly trying to achieve that noble gas-like stability, and their struggles, their alliances, and their battles create every substance we know. But not all elements are so straightforward. In the middle of the table, stretching from columns 3 to 12, you'll find the Great Plains, the transition metals. These are your familiar metals: iron, copper, silver, gold, titanium. They have a frustratingly complex chemistry. Unlike the elements on the edges, they start filing their electrons into inner shells, called D shells. They hide their extra electrons away, burying them deep inside. This means that as you move across a row of transition metals, adding 1 electron at a time, their outward personality doesn't change much. The new electron is tucked away, shielded from the outside world. This is why so many metals look and act alike. They're all cold, gray lumps because their outer electron structures are nearly identical. They are the conformists of the periodic table. Then you have the elements in those 2 rows at the very bottom, the lanthanides and the actinides. These are the rare earth elements and the heavy radioactive ones. They bury their new electrons even deeper, sometimes 2 energy levels down. This makes them almost indistinguishable from one another. Trying to separate one lanthanide from another is one of the most tedious and maddening tasks in all of chemistry. One chemist in New Hampshire spent years performing the same chemical process 15,000 times by hand, just to get a mostly pure sample of the element thulium. It's like trying to tell the difference between 2 grains of sand from the same beach. This architecture, the electron shells, drives the chemistry. But to truly understand the elements, we have to look deeper, into the nucleus, the heart of the atom. And here, we meet one of the most unlikely heroes in the story of science, a woman named Maria Geppert-Mayer. Born in Germany in 1906, Geppert-Mayer faced constant barriers because she was a woman. Universities refused to pay her, giving her stereotypically feminine work, like figuring out what causes colors. For decades, she was a scientific nomad, following her husband from university to university, an unpaid but brilliant mind lingering on the sidelines. It wasn't until after World War II that she began her work on the nucleus, the dense core of protons and neutrons that gives an atom its identity. She tackled a simple but profound mystery. Hydrogen, the simplest element, is the most abundant in the universe. Helium, the second simplest, is the second most abundant. But the third most common element isn't lithium, number 3, It's oxygen, element number 8. Why? Geppert Mayer had a hunch. She saw a parallel to the incredible stability of the noble gases with their full electron shells. She proposed that protons and neutrons in the nucleus also sit in shells, and that filling these nuclear shells leads to extraordinary stability. She called these magic nuclei. The magic numbers for protons or neutrons are 2, 8, 20, 28, 50, and 82. Notice that oxygen has 8 protons and 8 neutrons. It is doubly magic, making its nucleus eternally stable, which explains why it's so abundant. Calcium, with 20 protons, is another magic element, explaining why it's so common on Earth and why our bodies use it to build our bones. Geppert Mayer's theory was brilliant, explaining the very fabric of matter. Yet when the local newspaper announced she had won the Nobel Prize in 1963, the headline read, SD. Mother wins Nobel Prize. A demeaning title, perhaps, but a testament to a quiet genius who saw a hidden order in the universe that no one else had. The periodic table is read not just left to right, but up and down. Elements in the same column are like family members, sharing a common heritage. Let's look at column 14, the family of carbon. Carbon is the element of life. It's in the 6th position, meaning it has 4 electrons in its outer shell. It needs 4 more to be stable, which is a lot to ask for. So instead of stealing, carbon shares. It forms up to 4 steady, stable bonds at once, allowing it to build the long, complex chains and rings that form the backbone of every protein, fat, and sugar in our bodies. It is the ultimate connector, the socialite of the elements. This ability to form complex structures is what allows for the longest words in the English language. Proteins are long chains of amino acids, all built on carbon backbones. Biochemists have a system for naming them by stringing together the names of the amino acids. In 1964, the full chemical name for a protein in the tobacco mosaic virus was published. It is an anaconda of a word, running 1,185 letters long, acetylsyryltyrosylxerylisolucyl, and so on. It's a testament to carbon's incredible ability to build. Now, look directly below carbon on the table, and you'll find its closest chemical cousin, silicon. Silicon, element 14, also has 4 electrons in its outer shell, just like carbon. This has made it the great hope of science fiction writers for generations. If life could be based on something other than carbon, silicon would be the prime candidate. But silicon, for all its similarities, is not carbon. It's a bigger, bulkier atom. While it can form chains, it can't bend and contort itself into the rings that form sugars, which store energy for life. And when silicon bonds with oxygen, it doesn't form a gas like carbon dioxide, which we can breathe in and out. It forms silicon dioxide, sand. A solid. Imagine trying to build a life form that breathes sand. It just doesn't work. While some primitive creatures on Earth use silicon for structural support, like sea urchins with their silicon spines, it seems that carbon's unique flexibility makes it the only element truly up to the task of creating life as we know it. This column, this family tree, tells a story of changing character. Below carbon, the giver of life, and silicon, the foundation of our digital world, you find germanium. Germanium is the forgotten hero of the computer age. In the 1940s, scientists at Bell Labs were trying to replace the big, hot, fragile vacuum tubes that ran early computers. They needed a semiconductor, a material that could control the flow of electricity. The first successful device, the transistor, wasn't made from silicon. It was made from germanium. For a few years, germanium was the star. But it was temperamental. It overheated easily. And silicon, the main component of sand, was, as the saying goes, cheaper than dirt. At a trade show in 1954, An engineer from Texas Instruments demonstrated a silicon transistor that could play a record while submerged in boiling oil, a feat a germanium transistor could never accomplish. In that moment, the industry shifted. Germanium was abandoned, and Silicon Valley was born. Germanium did all the hard work, and silicon became the icon. As you continue down column 14, the family resemblance fades even more. Below germanium, you find tin, a dull metal used for cans, and at the bottom, lead, a metal toxic to life. It's a powerful reminder that while family members may share traits, small differences can accumulate over generations, leading to vastly different destinies. Every family has its stories, its heroes, its black sheep. And the families of the periodic table are no different. To truly understand them, you have to know the stories of the people who discovered them. The history of the periodic table is a story of human ambition, and its main character is a wild-bearded, fiery Russian named Dmitry Mendeleev. Born in Siberia, the youngest of 14 children, Mendeleev's life was one of hardship and brilliance. After his father went blind and died, his mother took over a local glass factory to support the family. When the factory burned down, she pinned all her hopes on her gifted son. She rode with him on horseback for 1,200 miles across the frozen Ural Mountains to a university in Moscow, which rejected him. Undaunted, she rode another 400 miles to St. Petersburg, where he was finally accepted. She died soon after. Mendeleev became a professor and, in 1869, did something that would change science forever. He was writing a chemistry textbook and needed a way to organize the 62 elements known at the time. He wrote each element's properties on an index card and began playing a sort of chemical solitaire. He arranged them by increasing atomic weight, but he noticed that their properties repeated in a periodic pattern. He laid them out in a grid, with elements of similar character in the same columns. He wasn't the only one to notice this pattern. 6 other scientists independently came up with similar tables. But Mendeleev was different. He had a deep, intuitive knowledge of the elements, and he was audacious. While other scientists were timid, Mendeleev was bold enough to leave gaps in his table. He declared that these were not mistakes, but placeholders for elements that had not yet been discovered. He went even further, predicting the properties of these missing elements, their weight, their density, their color. He even gave them provisional names, using the Sanskrit word for beyond, eka aluminum, eka silicon. It was an act of incredible scientific arrogance. And it turned out to be right. In 1875, a French chemist named Paul-Émile Lecoq de Bois-Baudran discovered a new element. He named it gallium, after the Latin name for France. When Mendeleev read about it, he realized it was his predicted eka aluminum. He even wrote to the Frenchman, telling him, with no justification, that he must have measured its density wrong, because it didn't match his prediction. The Frenchman, annoyed, remeasured. And Mendeleev was right. The scientific world was stunned. A theorist in Russia had seen the properties of a new element more clearly than the man who had discovered it. This triumph cemented Mendeleev as the father of the periodic table. His table was not just a catalog, it was a predictive tool, a law of nature. The discovery of gallium is a story about the dance between theory and experiment. But it's also a story about human pride. Lecoq de Bois-Baudran, the discoverer of gallium, was a master of the spectroscope, a device invented by the German chemist Robert Bunsen. Bunsen, famous for the burner that bears his name, was a pioneer in using light to study elements. He found that each element, when heated, emits a unique spectrum of colored light, like a chemical fingerprint. This allowed scientists to identify new elements with unprecedented accuracy. Lecoq de Bois-Baudran was the best spectroscopic surgeon in the world. And gallium, his prize, had a secret personality. It's a solid metal, but it melts at just 84 degrees Fahrenheit. As we discussed, a spoon made of gallium will vanish in a cup of hot tea. It's a prank that reveals the playful, deceptive nature of the elements. But not all discoveries were so playful. The periodic table has a dark side, a poisoner's corridor of elements that are masters of deception and destruction. The stories of these elements are cautionary tales about how chemistry can be turned to evil ends. Cadmium, element 48, sits just below zinc on the table. The two metals are often found together in the earth, and the body can mistake one for the other. Zinc is an essential mineral. Cadmium is a poison. In the early 20th century, a mining company in Japan began dumping cadmium sludge into the Jinzu River. The cadmium seeped into the rice paddies downstream. Local farmers, especially women, began to suffer from a mysterious and agonizing disease. Their bones softened and snapped under the slightest pressure. Their kidneys failed. Their cries of pain gave the disease its name, ite, or ouch disease. The cadmium was replacing the calcium in their bones, turning their skeletons into brittle chalk. To the right of cadmium, you find the most horrific elements on the table. Thallium, element 81, is known as the poisoner's poison. It's tasteless, odorless, and dissolves in water. The body mistakes it for potassium, another essential mineral, and absorbs it readily. Once inside, it wreaks havoc, unstitching proteins and causing a slow, painful death. Its most famous calling card is hair loss. It has been the weapon of choice for spies, assassins, and serial killers throughout history. These heavy metals are so poisonous because they are subtle. They are not violently reactive like sodium. They can sneak deep into the body, mimicking essential nutrients, before they begin their destructive work. They are the imposters of the periodic table. The elements have not only been weapons of murder, but weapons of war, shaping the course of global conflicts. World War I is remembered for its brutal trench warfare, but it was also the first chemical war. It began with bromine, a halogen that causes searing tears. The French first lobbed bromine shells at the Germans in 1914, but the gas was ineffective. The real architect of chemical warfare was a German chemist named Fritz Haber. Haber was a genius, a man who could have been one of the greatest saviors in human history. Around 1900, he figured out how to pull nitrogen, which makes up 80% of our atmosphere, out of the air and convert it into ammonia. This process made the mass production of artificial fertilizers possible. Haber's invention has been credited with feeding billions of people, saving countless lives from starvation. He won a Nobel Prize for it. But Haber's motives were not entirely humanitarian. He developed the process to help Germany create nitrogen-based explosives. When World War I broke out, he eagerly volunteered to lead Germany's poison gas division. He ditched bromine and turned to its nastier cousin, chlorine. Chlorine attacks the lungs, causing victims to drown in their own fluids. Haber personally directed the first successful gas attack in history, which left 5,000 French soldiers scarred and dying in a trench near Ypres. His wife, Clara Immerwahr, also a brilliant chemist, was horrified by his work. She begged him to stop. He ignored her. After he returned from Ypres, he threw a party to celebrate his new weapon. That night, she took his army pistol, walked into the garden, and shot herself in the chest. Haber left the next morning to direct more gas attacks on the Eastern Front. Haber's is one of the most tragic and complicated legacies in science. He was a Jew who converted to Lutheranism to advance his career, a patriot who developed weapons for Germany, and a man whose scientific brilliance was used for both immense good and unimaginable evil. The Nazis later exiled him for his Jewish roots, and he died in 1934. In a final horrifying twist of irony, the chemical company he worked for later manufactured Zyklone B, the insecticide gas used to murder millions of people, including some of Haber's own relatives, in the concentration camps. Warfare is also driven by metals. During World War I, Germany's most feared weapons were its Big Bertha siege guns, massive cannons that could hurl shells for miles. The intense heat of firing these guns warped their steel barrels. The famous Krupp Armament Company found a solution: spiking the steel with molybdenum. Molybdenum has an incredibly high melting point, making the barrels far more durable. But Germany had no supply of molybdenum. The only known source was a mine in the Rocky Mountains of Colorado. A German-owned mining company waged a secret war to seize control of the mine, sending in claim jumpers to harass the American owner, threatening his family, and even throwing him off a cliff. He survived, but the Germans got their molly be damned, and for years, they shelled Paris with guns made stronger by an element secretly mined in America. In World War II, the it metal was tungsten, which sits below molybdenum on the table. It's even harder and has a higher melting point. The Nazis coveted tungsten for armor-piercing missiles. The primary supplier was supposedly neutral Portugal. The dictator, Antonio Salazar, played both sides, selling thousands of tons of tungsten to both the Allies and the Axis, leveraging his country's near monopoly to make immense profits. Much of the gold the Nazis looted from their victims, including gold fillings from the teeth of gas Jews, was laundered through Portuguese banks to pay for the tungsten that fueled the German war machine. The story of the elements is not just written on Earth, it's written in the stars. For centuries, we believed that the elements have always existed, that they were created with the universe. But in the 1950s, a handful of astronomers, including a brilliant and eccentric man named Fred Hoyle, realized that stars are the great forges of the cosmos. The universe began as a slurry of hydrogen, with a bit of helium. Gravity pulled this hydrogen together into stars. The immense pressure inside a star's core fuses hydrogen atoms together to form helium. This is the process that powers every star in the sky, a slow, steady burn that can last for billions of years. But when a star runs out of hydrogen, things get interesting. The star, desperate for fuel, begins to fuse helium into heavier elements, carbon, oxygen, all the way up to iron. Each new stage of fusion buys the star a little more time, but the end is near. Iron, element 26, is the end of the line. Fusing iron doesn't release energy, it consumes it. An iron core is a star's death sentence. So where do the elements heavier than iron come from? Gold? Lead? Uranium? They come from the most spectacular events in the universe, supernovae. When a massive star runs out of fuel, it collapses under its own gravity in a matter of seconds. Then, it rebounds in a cataclysmic explosion. For one glorious month, a single supernova can outshine an entire galaxy of a billion stars. In this inferno, so many particles collide with so much force that they overcome the energy barrier of iron. They fuse onto iron nuclei, creating every element and isotope up to uranium, and spewing them across the galaxy. One such explosion, about 4.6 billion years ago, seeded our corner of the cosmos with the elements that would become our solar system, our planet, and us. As the great astronomer Carl Sagan so beautifully put it, we are all star stuff. This cosmic dust cloud coalesced, with the sun at its center. Lighter elements were blown to the outer edges, forming the gas giants. Jupiter, the largest, is a failed star. If it had been just a bit more massive, it might have ignited fusion, and we would live in a binary star system. Even as a planet, its immense gravity and pressure create exotic forms of matter, like oceans of liquid metallic hydrogen. Scientists even theorize about neon rain, droplets of liquid neon falling through its atmosphere, lighting up the Jovian sky with streaks of brilliant crimson. The rocky inner planets, including Earth, formed from the heavier elements. As the molten earth churned, dense iron sank to the core. Lighter elements rose to the crust. But how do we know this history? How do we know the age of the Earth? The answer lies in the slow, steady decay of radioactive elements. The heaviest elements, like uranium, are unstable. Over billions of years, uranium breaks down into lead. By measuring the ratio of uranium to lead in the oldest rocks on Earth, a determined scientist named Claire Patterson, in the 1950s, was able to calculate the age of our planet, 4.55 billion years. But Patterson's work had an unintended consequence. To get an accurate measurement, he had to create an ultra-clean laboratory, free from any lead contamination. In doing so, he discovered that our entire planet was covered in a fine dust of industrial lead, primarily from leaded gasoline. His horror over this contamination turned him into an activist, and his crusade is the main reason we no longer have lead in our paint or our gasoline. The elements don't just tell us the history of our planet, they tell us about the cataclysms that have shaped it. 65 million years ago, the dinosaurs vanished. In the 1970s, a father-son team, Louis and Walter Alvarez, were studying limestone deposits from that era. They found a thin, unaccountable layer of clay that contained 600 times the normal level of the element iridium. Iridium is rare on Earth's surface. Most of it is locked away in the iron core. But it's common in asteroids. The Alvarezes proposed that a massive asteroid, the size of a metropolis, struck the Earth, throwing up a cloud of iridium-rich dust that blotted out the sun and caused a mass extinction. The discovery of a 100-mile-wide crater on the Yucatan Peninsula, dating to exactly that time, seemed to prove their theory. The quiet testimony of a single element had solved one of the greatest mysteries in Earth's history. The stories of discovery are filled with brilliance, but also with mistakes, some of them monumental. Emilio Segre, the man who finally hunted down the elusive element 43, technetium, made one of the biggest blunders in the history of nuclear physics. He was working with the legendary Enrico Fermi in 1934 when Fermi announced he had created the first elements beyond uranium. It turned out Fermi had actually been the first person to induce nuclear fission, splitting the uranium atom, and hadn't realized it. Years later, Segre, having learned this lesson too well, was asked to analyze a sample that was thought to be a new transuranic element. He dismissed it as just another fission product. That sample contained neptunium, the first true transuranic element, and the colleague who asked for his help, Edwin Macmillan, went on to win a Nobel Prize for its discovery. But perhaps the most famous mistake belongs to the man many consider the greatest chemist of the 20th century, Linus Pauling. In the early 1950s, the race was on to discover the structure of DNA, the molecule of life. Pauling, a two-time Nobel laureate, was the odds-on favorite. Working with sketchy data, he rushed to publish a model. He proposed that DNA was a triple helix, with a phosphate backbone at its core. Across the Atlantic, two young, unknown scientists named James Watson and Francis Crick got a copy of Pauling's paper. They were stunned. They had built the same model a year before and had been told it was wrong. They knew Pauling had made a fundamental error. The negatively charged phosphate groups in the core would repel each other, blowing the molecule apart. Knowing Pauling would soon realize his mistake, they scrambled. Using a crucial piece of X-ray data from a colleague, Rosalind Franklin, they built a new model, a double helix, with the phosphates on the outside. They published their work in April 1953, beating Pauling to the greatest biological discovery of the century. Pauling, to his incredible credit, admitted his mistake with grace and championed their model. The periodic table is not just a tool for chemists, it's a source of inspiration for artists. The poet Robert Lowell, one of the great mad geniuses of his time, suffered from debilitating manic depression. His life was a chaotic storm of brilliant creation and self-destructive behavior. In the 1960s, he began taking a new drug, a simple salt of the element lithium. Lithium is a mood stabilizer. It works by resetting the body's internal clock. In manic depressives, this clock runs wild, independent of the sun, leading to euphoric highs and crushing lows. Lithium helps regulate the proteins that control this clock, tethering the mind back to a normal 24-hour cycle. The drug transformed Lowell's life. He became stable, calm. But his poetry changed. It grew less polished, less wild. He once said to his publisher, "It's terrible, Bob, to think that all I've suffered, and all the suffering I've caused, might have arisen from the lack of a little salt in my brain." The story of Lowell and lithium is a poignant reminder that our highest faculties, our creativity and our madness, are rooted in the simple chemistry of the elements. As we reach the bottom of the periodic table, the elements become strange and fleeting. These are the man-made elements, created one atom at a time in particle accelerators. The discovery of these elements became a new theater for the Cold War, a fierce rivalry between a team at the University of California, Berkeley, led by Glenn Seaborg, and a Soviet team at a lab in Dubna, Russia. For decades, they battled for priority, for the right to name a new piece of the universe. The Berkeley team named elements after their university berkelium and state californium. The Soviets named one after their lab dubnium. In a moment of scientific magnanimity, the Berkeley team named element 101 mendelevium, in honor of the great Russian chemist. But the truce didn't last. The dispute over who discovered elements 104, 105, and 106 dragged on for 30 years, long after the Cold War had ended. In the end, Berkeley won the right to name element 106 Seaborgium, after their leader, the only time an element has been named for a living person. And what of the future? Where does the table end? The elements get more unstable as they get heavier. But physicists theorize about an island of stability, a cluster of super-heavy elements around element 114 that might be surprisingly long-lived. Reaching this island is one of the great quests of modern physics. But there may be a hard limit. Richard Feynman, another brilliant physicist, calculated that around element 137, the laws of physics as we know them begin to break down. The inner electrons of such a massive atom would have to travel faster than the speed of light, which Einstein's theory of relativity forbids. At this point, the irresistible force of quantum mechanics meets the immovable object of relativity. What happens then? No one knows. This undiscovered element, 137, is sometimes called Feynmanium. It represents the edge of our knowledge, the point where our map of the universe goes blank. The periodic table we know, the familiar castle shape, is just one possible arrangement. Scientists have designed over 700 variations, spirals, helixes, pyramids. And our understanding of what an element is continues to expand. Scientists can now create superatoms, clusters of atoms of one element that mimic the chemical properties of another. 13 aluminum atoms can band together and act just like a single atom of bromine. They are exploring quantum dots, virtual atoms made not of a single nucleus, but of a collective of thousands of atoms acting as one. The story of the elements is far from over. The periodic table is not a finished work, but a living document, a story that is constantly being written and rewritten. It is a testament to human curiosity, to our unending quest to understand the world and our place in it. From a simple disappearing spoon to the birth of stars, from the poison in an assassin's vial to the salt that calmed a poet's mind, the elements are the characters in the epic story of our universe. And it's a story that is all around us, and inside us, waiting to be read. Commentary. After a journey like that, through Sam Kean's The Disappearing Spoon, it's hard to look at the world in the same way. What I find so powerful about this book is how it transforms something we all thought we knew. That boring chart from chemistry class? into something deeply personal and alive. It's a profound shift in perspective. The greatest lesson, I believe, is that science is not a collection of cold, hard facts. It is a human endeavor, driven by the same passions, flaws, and flashes of brilliance that define all of human history. We see the ambition of Mendeleev, risking his reputation on a bold prediction. We see the tragic patriotism of Fritz Haber, whose genius both fed the world and gassed it. We see the quiet perseverance of Maria Geppert-Mayer, a brilliant mind overlooked for decades simply because she was a woman. These aren't just stories about science, they are stories about what it means to be human. The periodic table becomes a mirror, reflecting our capacity for incredible discovery and terrible destruction, for generosity and for greed. Kean reminds us that the world is so much more intricate and fascinating than it appears on the surface. We walk around every day, breathing air, drinking water, using technology, and rarely do we stop to consider the incredible stories of the atoms that make it all possible. The oxygen we breathe was forged in the heart of a dying star. The silicon in our phones was at the center of a scientific rivalry that created the modern world. The lithium in a battery might be the same element that saved a poet's life. The book gives us a new lens through which to see the hidden wonder in the mundane. It connects us to the grand, cosmic story of the universe, and at the same time, to the intimate, personal stories of the people who shaped our understanding of it. So, how can you apply this? What can you take away from this today? It's actually quite simple. The next time you encounter the periodic table, whether it's in a textbook or just a picture online, don't just see it as a scientific tool. See it as a library of stories. Pick an element, any element. It doesn't have to be a famous one like gold or uranium. Pick something obscure, like dysprosium or praseodymium. And just get curious. Spend 5 minutes looking up its story. Who discovered it? Where does its name come from? What strange, unexpected role has it played in the world? By doing this, you're not just learning a fact. You are practicing the very essence of what this book teaches, that curiosity is the engine of discovery, and that everywhere you look, there is a story waiting to be found. You begin to see the world not as a collection of objects, but as a web of interconnected histories. That's a powerful way to live, to be constantly surrounded by wonder. You start to realize that the history of the world isn't just in history books, it's written in the very atoms that make up the world itself. That was a summary of The Disappearing Spoon by Sam Kean. We've touched on some of the most captivating tales today, but I'll be honest with you, a summary is just a glimpse through a keyhole. The real magic happens when you open the door and explore the rooms yourself. The book is filled with hundreds of other stories, each one as fascinating as the last. This summary is designed to help you decide if this book is worth your time. If anything we've talked about has sparked your curiosity, I wholeheartedly encourage you to grab a copy. Reading it isn't just about learning. It's an experience that can genuinely change the way you see the world and the history woven into every single thing around you. The link to the book is in the description. Also, if you found this journey valuable, please take a moment to click that like button and subscribe to our channel. That way, you won't miss our next exploration into another life-changing book from the billionaire's bookshelf. Let's continue to grow together.